In this section, we'll learn about a graphical technique for analyzing autonomous differential equations. Notice we're only working with autonomous differential equations in this section. This graphical technique is called a phase plot. Let's consider the autonomous differential equation dn dt equals n times n minus 1 times n minus 3 times n minus 5. Although the derivative dn dt is a function of t, and that's because n is a function of t. Remember, the shorthand math notation for saying that is to say n equals n of t. But if you prefer, you can write n is a function of t. Therefore, the derivative of n also depends on t. But notice that the independent variable t does not appear in the formula for dn dt. In fact, that's what makes this an autonomous differential equation. Since the formula for dn dt only has n's and not t's, we can think of dn dt as a function of n, with the t sort of acting in the background, out of sight. To make this easier to remember and visualize, I'm going to call the derivative n prime. I'm not even going to call it n prime of t. So instead of n prime of t or dn dt. Basically, I want to get that t out of our sight because we're not going to be thinking about it right now in this section. We will now graph n prime as a function of the dependent variable n. This type of graph is called a phase plot. Here's the graph of n prime. The vertical axis is the n prime axis, and we're plotting n prime as a function of n, so the n axis will be the horizontal axis. And I just want to emphasize this is the graph of n prime, not of n. So we're not looking at the solution graph here, we're looking at a graph of n prime. The key realization here is that where n prime is positive, in other words, where the graph of n prime is above the horizontal axis, n itself will be increasing. Let's take a look at a few sample population values and what will be happening with them. Suppose the population happens to be 2, and it's happening at some time, but we don't know anything about time and we're ignoring it. So I look at the sign of the derivative. This height here is n prime when n equals 2. I don't want to call it n prime of 2 really, because that'll make it sound like the time is 2, and that's not what we're saying. We're saying that n is 2. Notice that is a positive number, therefore we know that n is increasing when n equals 2. And we can denote that on our horizontal axis by putting a little arrow to the right. So now we're somewhere over here, say at 2.5. what's the population n going to be doing then? Well, again, we look at the graph of n prime to see that n prime is positive when n equals 2.5. So the population is still increasing. And in fact, it's always going to be increasing on that section, because if you look up at the graph of n prime, it's positive all along here. And similarly, starting from 1, the population is going to be increasing because the derivative is positive there. That's also going to be happening over here at 5. Positive derivative, so increasing function. On the other hand, where n prime is negative, in other words, where the graph of n prime is below the horizontal axis, n itself will be decreasing. Let's put arrows on our n-axis to indicate that. So in this whole section from 0 to 1, the derivative graph is below the horizontal axis, for the function is decreasing. And remember, this graph is not the graph of n, it's the graph of n prime. And then we've got a section going from 3 to 5, where again the derivative graph is below the x-axis, which means the derivative is negative, which means the function would be decreasing. So although we don't have the graph of n, in fact we can't graph n right now because we don't have a formula for n, we can at least put on the n-axis what direction it would be moving.